Well, good morning, good afternoon, and good evening, everyone. Welcome back. Okay, so we are getting very near the end. The proof that OCA implies all automorphisms of the Kalkin algebra inner is almost over. We are getting there, and we have just a few classes left. So let me just remind you once again, there will be no classes next week. I had some conference scheduling. Is going to be very intensive, so there is no point in trying to teach. But then we are back the week after, and unless I made the wrong calculation, the week after is our last week. The semester at York and in Canada lasts for 12 weeks, and it will be the 12th week of classes. So I'll basically just have a little bit more time to finish the proof that we're doing right now, and to do a little bit more, basically, essentially, I'll just try to convince you that there is much more than I would have done. Then you would perhaps want to know. Not only that I would want to do that, but that they would you would probably want to listen to learn. Anyway, so let's go back to class. One more announcement. Assignment number 4 is online. It's due in 2 weeks as usually, and it is the last assignment. And don't forget, if you're taking this course for credit, if you haven't done already so, you should contact me so that we can arrange for you to pick a topic for presentation. Presentations will be taking place in the last class. And let's just see, last class, that would be Friday, April 9th. Actually, I'm still thinking whether to have presentations then or just to have a separate meeting for presentations only. Let's not worry about that yet. So it's in distant future still. So let's not think about that. All right. So let's go back to where we took off last time. So we are proving that OCAT implies that phi, and phi is of course automorphism of the Kalkin algebra, has a sigma narrow epsilon approximation on the x of E. I'll remind you of the definitions in a moment. And also something that I owe you from the last time. So I promised to give you an example of an endomorphism of L infinity mod C0 with a sigma narrow lifting but no continuous lifting. Well, it turns out actually I cannot do that. What I can do is instead of C star algebra, do this analogous thing for Boolean algebra. So look at the power set of natural numbers modulo phi, the Frechet ideal. There is such an example, but let's talk about it after. So let's go back to number 1. You see, this is in some sense proof of this lemma that we started last time is central in the entire proof, because that's really the point where part of the magic happens, where we just start from some arbitrary automorphism, and at the end of the day we have something that starts looking more definable. I do think that it was a good idea to do proof in 2 installments, because basically we'll have opportunity to go over the first part once again, and hopefully it will settle better. All right, so let me first remind you of our weapon of choice. It is OCA infinity, which is axiom stated here. So it says that whenever we have a separable metrizable space X and a sequence of open colorings, remember open coloring means that the first color is open, and that sequence is decreasing, the open parts are decreasing, then one of the 2 alternatives applies. Alternative number 1 says that there is a function f from the Cantor set. So here's Cantor set 2 to n. I'm writing 2 for the set 0, 1, right? It was von Neumann's idea after all. So f maps 2 to n into x. And it has the property that for any 2 actually F maps an uncountable subset of the Cantor set into X. And for any two elements of that set, the closer they are, namely the bigger this delta of those two elements is, the closer their images are in the sense of these open partitions. So that they are, the closer points are, the smaller that open bit, the higher its index is that those 2 points belong to. And the second alternative is that we can cover X with countably many sets so that each one of them is homogeneous for one of these closed colors. As I said last time, the fact that these indices agree is a red herring, really. You can always play with it and re-enumerate them. It just matters that each of the sets is homogeneous for something, so for one of these closed colors. And importantly, OCAT implies OCA infinity by result of Justin Moore. So using this is the same as using OCAT. And here are the definitions from the last time. We consider the unit ball of B of H with respect to the weak operator topology, so it's compact metric space. And now here, we say that subset Z of the unit ball cross the unit ball is narrow. Okay, so here is Z. So it's narrow if each of these sections, here is little a and here is the section, each of these sections is compact. It's included in a single class module of the compact operators. And it's epsilon narrow if each of the classes is such that when you move it to the Calkin algebra, then its diameter is at most epsilon, right? So this B epsilon KC means that the image of B minus C under the quotient map has norm at most epsilon. Right, so zero narrow is the same as narrow. And now sigma epsilon narrow means that the graph can be covered by a countable family of epsilon narrow Borel sets. Right, so Z may be kind of big, but there are countably many Borel sets. Each one of them is epsilon narrow, and their union covers this our set. And finally, the reason why we are looking at this, we're looking at liftings, right? So we have our phi is a function from Q of H to Q of H. Now, if you look at lifting of phi, it is a function from B of H to B of H. So its graph looks like this. But again, we just look at the unit ball. Right, that's all that matters really. And we say that phi has a sigma narrow lifting if this restriction to unit ball has a sigma narrow lifting. Namely, if you look at the graph of this lifting phi star, you can cover it by countably many narrow Borel sets. And similarly, sigma narrow epsilon approximation is defined in a similar way. And finally, lifting on D of E or on D of E, remember, difference between these two is that this one is discrete, is discretization, and this one is a von Neumann algebra. And okay, so as I said, we'll go back to the example that I failed to give you last time. I'll give you a different example this time. Okay, so here is the lemma that I started on Friday. So lemma says, assume OCAT if phi is an endomorphism of Q of H and epsilon is greater than 0, then phi has a sigma narrow epsilon approximation on dx tilde of E for some infinite x tilde. Right, so I should say here, for every E in part N. Right, so you give me phi, you give me E, and you allow me to use OCA, then I can produce an infinite set and sigma narrow epsilon approximation. And here is in short, once again, what that means, there is a function theta. So theta maps the unit ball to the unit ball. And part A says that theta is really a lift of phi. Actually, not lift, epsilon approximation of phi. So it's only up to epsilon. Is theta correct? And second part says that we can cover it by a countable family of Borel sets called Zn. Right. So we started the proof last time, and we actually came to a natural stopping point for that proof. So let's just before I remind you, do you want the sets Zn to be narrow? Yes, I do. Yes, I do. Thanks, Pedro. Did I forget to? Of course. Why did I? Okay, we'll get them. We'll get them to be narrow. Actually, epsilon narrow, not narrow. Yeah, sure, of course. That's not automatic by any means, because you can just take Borel set B of H cross B of H, right? That would make it vacuous. Yes, thank you so much. Yeah, definitely. All right. So here are conventions that we introduced last time, just a quick refresher. So first, we index the intervals of our E by finite binary sequences, because this tree structure of those sequences will be useful. So E is E sub S for S in 0, 1 to less than N. Each E sub S is an interval. Now, before we had consecutive intervals, here they are all around the place, but that doesn't really matter. You know, infinite is infinite. Infinite is going to be cofinal in N. And we want our E to have this property. So, so actually, when I said, okay, so what I wrote on the previous slide is technically correct. We'll get it for every E, but the point is that we'll get this. Yeah, actually, it's an exercise. It is equivalent. It may not be obvious, but let's not waste time on that. So I can basically join intervals in E to make them longer and assure that this property holds. Remember what that property means, and what really it means to us is that no matter how I choose a branch in 2 to N, along this branch, if I look at E sub S's indexed along the branch, the lengths are increasing to infinity. That is what we want. Now, if X is a subset of this tree, and if it happens to be included in a single branch, and if it's infinite, it determines this branch uniquely, and we denote this branch B of X. And finally, we fix a discretization of D of E. Right, so we have compact metric space there. All right, so now here is the proof. So we fix D, which is big enough. Big enough means at least 1 over 2 epsilon, and we fix an N. Actually, no, we don't fix an N yet. So I'm not sure what this N is doing here. We'll fix N later on. Now, here is the X. X is the set of all pairs XA such that the B of X is defined and A is in D of X. Right, so X's are these branches, or rather subsets of branches of this tree, and A's belong to discretization. And now we topologize X in the following way. So this is what you always do when you're using OCA. You're trying to somehow make some wild object definable to get some closed set which approximates it some way. Well, you have to define topology as to reflect the structure of this object. You see, there is a natural topology here, right? X is really a subset of a countable set, so it's a Cantor set, and A is also an element of Cantor set. So X is a naturally including Cantor set, but that natural topology is not good enough. You want much finer topology, which takes into the account, okay, the branch B of X, that's not a big deal, that's almost automatic, but these two here, Q sub X, remember Q sub X is phi star of P sub X. And P sub x is the projection to the span of all those basic vectors whose indices are in the intervals that belong, whose indices are in the intervals indexed by x, right? So it's a union of union, and phi star of A is there. So basically, these two objects here are completely unrelated to the first three objects a priori. They are just given by some random, some application of the axiom of choice, in which we picked this lifting. And the point is that if you refine topology by this, we are going to get quite something there. So this is belongs to this compact metric space, actually, right? So this is a definitely separable metric space, and the topology, as I said, is due to Veličković. Basically, it's a descendant of partition due to Veličković, and here it is. So here, right. So for every n, so n here is a variable, and n greater or equal than 1, say. We take two elements of x, and they belong to this open coloring if three conditions are satisfied. First one is that x and y determine distinct branches. Second is that A and B agree on this small part where their branches agree. And the third condition is that unlike A and B, their images disagree as badly as 1 over D, and also badly in another way after nth index. Projection P, right, so P is the same as Px, so it comes from this approximate unit for the compact operator. So these are the complements of those projections. Right, so last time, we checked, this is the same partition once again. Last time we checked that this partition is indeed open with respect to this finer topology. And second, we checked that this first alternative of OC infinity fails for that partition. And now it remains to see that the second alternative gives us what we needed to give us. All right. So here, so OC infinity implies that there are M1Dn homogeneous sets, XDn. So XDn is subset of X for each n, and X is subset of X is covered by those sets. Now, you see, as always, when you're applying OCA, you can take closure of one homogeneous set. It is still one homogeneous. So, so XDNs are closed subsets of that set, which was product of 3 copies of Cantor set in different varieties, with 2 copies of the unit ball of B of H in weak operator topology. So we have this closed subsets of compact metric space, countably many. And those closed sets are telling us something about our function. And then our problem is, of course, that when you take closure, that basically means that some garbage enters your sets, but we need to extract the gold out of that garbage. And that's what this proof is about. All right, so here is, again, now here, what you have written is not what is M1, but sorry, you don't have what is M0, but what is M1. Right, so the complement of M0, because now we have M1 homogeneous sets. Now, here it is. So you see, M0 was very small because it was conjunction of 3 conditions. Here we have disjunctions of the negations of those 3 conditions. So XA and YB belong to M1D if either they determine the same branch, or, oops, this was supposed to be not equal, not less equal doesn't even make sense. Or they disagree on this, or if branches are different, they disagree on this common part, Or if both of those two conditions hold, then that they agree up to 1 over d, and by multiplication in both sides as far as their images are concerned. So if you think about it for a moment, it's really this third condition that is the good condition. It is the gold in some sense that I referred to in a moment ago. And first two conditions are kind of annoying. So we'll have to somehow work around them to see what to do. Okay. So here we have these homogeneous sets which cover X. And now here is what we have. So for distinct XA and YB in X, and for K in N, so I'm introducing a new parameter here. A second, here. We write delta, right? So I'm abusing notation here. Use delta for something different, but there is a reason for using delta here because it really has the same meaning here. So delta of XA and YB is the minimal K such that either there exists some S in 0, 1 to K such that S is X delta Y. So basically, indeed, this is delta as before, the first place where X and Y disagree. Or second possibility, that same S belongs to the intersection of X and Y. However, A of S and B of S are distinct. Right, so remember, this S really gives you E sub S, and AS and BS are two projections. They're projections in PS, B of H, B of S in this corner. So this is a matrix algebra. And even less than that, they actually belong to this finite set, this discretization, so that they're different. Right. So this is what I think of as X A and YB disagreeing for the first time. And now one more thing, these projections P0K, this approximate unit, I'll be using it quite a lot. So I'll call them E sub K. So E sub K is this particular approximate unit for the compact operators. Okay, and here is another thing that we need to do. So for each n, you see, as I said, this XDN is a closed subset of compact metric space, so it's separable, and we can pick a countable dense subset. Right, so EDN is a countable dense subset in that topology that XDN is closed, right? In that topology, which takes into account QX and phi star and all that. Now, again, the closure of each one of these sets is N1DN homogeneous. Well, it's so because the closure is XDN. Now we fix. So now you see what is the point here. This EDN is countable. Cantor set has uncountably many branches. So there are many branches which are not in this set here, right? Because each of the EDNs is countable. There are countably many of them. If you look at all the corresponding branches, there are only countably many. And you can choose one branch that shoots on the side that is distinct from all of them. Right, so here are those branches, and here is B of X. Now, what is the reason for that? Well, you see, if you look at some XA, which has this property, that this is that its branch is BX, then this first condition here will not be an issue when you consider an element of one of these EDNs. Right. So let me just see. So this is B tilde. So let me just take a record on that. Note. So if B tilde is equal to Bx and XA is in XDN and YB is in EDN, then this condition M1 fails, then B of X different from B of Y. So if that condition fails, then we are narrowing it down further. Right, so actually it's here, right? So we know that XA and YB belong to M1DN. So if this fails, then it's one of these two conditions. Either, of course, not this condition, but the correct condition with a negation, right? So either PXB is different from PYA, or we have this here. And now we have to take care of the next condition. And that's the next thing. So okay, so on this slide, we have basically recap of what we've done so far. So here is the partition, here is the way we define delta, and here are these definitions. And all right, so we go. Now here the proof starts basically. We choose a finite subset of EDN, FKN, so for each K, I should say that. For each K, we choose a finite subset, which has the property that, let me try to draw this. So for every XA in EDN, right? So for every XA, so here is X and A is somewhere below X, there exists YB in FKN, I'm just drawing Y for now, which has the property that delta of XAYB is greater than K, and here is what it means. So it means that up to this point, not only X and Y, but also if you take into account A and B, everything agrees up to this point. And moreover, if you look at the following, look at phi star, actually, okay, this is, I use notation, this is called QX, this is QY. If you look at QX and QY, they're quite close. You see, EK is this here. So EK is the finite rank projection. Its range, if you look at it, it is a compact, I mean, its unit ball is compact in Hilbert space. So the set of operators here is compact again. Oh, that's right, it's compact, I want compact. So I want EK on the left-hand side as well, because otherwise it's not compact. Right, okay. So you have it on both sides. So I want phi star px to be approximated by phi star py arbitrarily well, and same with phi star a and phi star b. Right. So the point is that I have here a compact metric space, and in that compact metric space there is a finite 1 over k dense set. Right. It's totally bounded. So I'm using total boundedness of this compact metric space to pick a finite subset of EDN. Now, I was just asking for XA in EDN, but without loss of generality, actually not without, so the same holds for every XA in XDN, because EDN is dense in it, right? So I'm just using density of EDN for that. So in some sense, these FKNs are controlling what is happening with my set, right? So once again, okay. So if I scroll, you can see the partition. You see what happens right now. If I look at my FKN, it tells me what are the possibilities for elements XA below K. Below K means, in the tree, it means the obvious thing, and in the operator bit, it means that these two inequalities hold. Right. So I have these finite sets which completely control what is going on so far there. Sorry, this is the same thing. Yes. Okay. So now what we do? So right. So maybe I should add a page here. Right here. Okay. Okay, so what do I do? So for every, okay, actually first note, oops, this was the highlighter, that union of fkn's, n is fixed. Did I say that? I hope that I said that. So we fix an n. Right, so I'm just handling one of these sets. So union of fkn's is dense in xdn. Right, I chose them that way. Okay, so, and not only that, but if I just take union over any infinite set, so for every z subset of n infinite, again, union is going to be dense because I'm just basically guessing at later and later stages. Okay, so now I define k of j for j in n as follows. So first, k of 0 is 0. And I want kj plus 1 to be greater than kj. And I want it to have another property. Kj plus 1 is the minimal. Such that that we have the following: b tilde restricted to kj plus 1. Remember, b tilde was this branch which was off, which was leaving all those countable many branches. This is different from b of y restricted to kj plus 1 for all yb in the union and less or equal than k of j. Okay, I think I have a typo here. Let me just see this. This makes no sense what I have written here. Yeah, okay, no, I have a nasty typo here. Right, okay, so union of overall n less or equal than, it's not n, actually n is a very bad choice because n has been fixed, as you may remember. And j is not, okay, so I less or equal than k of j of f of in. Right, so let's see what is happening. I look at first finitely many sets. This is a finite set. Now, if I look at the finite set, there are only finitely many branches belonging to that set. Now, my branch b tilde, let's draw it in a different color. This branch b tilde, which is in green, it leaves that finite set. And therefore, it leaves each one of those finitely many branches at some fixed point. So I just need to go high enough to make sure that b tilde has left all of those branches. So, and that's my k of j. Actually, k of j plus 1. The one that I drew is just too big. So basically, you want to make sure that it is right after b tilde leaves the last one of those branches. Kj plus 1 is there. Right, so we just want to take rid of all noise, get rid of all the noise that is caused by overlapping between these. So now, I don't know if, I guess it's clear what I mean by this. B restricted to kj plus 1. So if this is kj plus 1, then this node here, maybe I should use a different color yet again. Let's say in blue. This is b tilde restricted to kj plus 1, right? So it is a node of this Cantor tree. Now, right, actually, I have no idea why am I using red color for this. I just started using it, and let me know if it's annoying. It might be annoying. Anyway, so once we choose it, right, so this defines us an increasing sequence of these KJs. Right, so again, what do we do? KJ is big enough to be bigger than sufficiently bigger than KJ minus one. Now we look at this FKJ, that set of all those elements which are sufficiently dense up to that point. Now, you see, the problem is that actually, let me draw that. Here, the problem is that if you take, I'm looking for a gray, I never use gray. So let's say if I have some Y, which belongs, let's say this is YC, and it is in some FLN, you know, basically, because this set is dense, I can find branches which are arbitrarily close to B. So there are branches which are not leaving B for quite a while. So, and those branches will come, we will show up in one of these sets FIN. So, so I need to take a bigger KJ plus one, KJ plus two, to be even higher than the places where those branches leave B tilde. Okay, and now we take X tilde, which is X tilde from the statement of the lemma, to be B tilde restricted to KJ plus one for all J in N. Right. So the way that this looks like is that we have B tilde. Right? K0 was just chosen randomly, just it's zero. It could have been anything. Right? K1 is big enough, K2 is bigger, and so on. K3 and so on. And we just take X to be this set of these nodes. And each node has the property that those finite sets are closed here, but by the time we get to K3, they all leave our branch B tilde. All right, so now we have another definition. Oh, okay, my iPad is at 14%, so I may have to run to get a charger at some point, but let's not do it right now. Now, fix YB in, okay, I'm using different font here. Right, actually, I should be using this font. So this is XDN, and fix K in N, and consider the following. W, Y, comma B, comma K is defined as follows. Set of all pairs AC in dx tilde cross B of H less or equal than 1, such that X tilde A belongs to XDN delta of X tilde A YB is greater than K, and the maximum of the norms of EK phi star B minus C EK, comma EK, it's QX tilde minus QY EK, maximum of those two is less or equal than 1 over K. Now, let's take a look at this set here. So what do we have? Note this element A is coming out of nowhere. It didn't appear in X. No, sorry. not A, I wanted to say C. I was looking at it wrong. So the C is coming out of nowhere. X tilde A is in our set. Right, so think of A as something in the domain of our function phi star. And C is a candidate. Let me write it down here. So C is a candidate for phi star of A. Basically, we are testing C. We are trying to see how does it make sense to send A there. And what is the evidence for that? Well, you see X tilde A belongs to XDN. Now, this delta of X tilde A and YB, right, so I should have said there exists, no, YB is here, right? YB is the same one here, right? So YB is an element here, and basically YB testifies, yeah, so far, as far as I can see, C looks like a reasonable candidate. So YB follows X tilde A for quite a while, up to K. And now the norms of these two, so you see EK, QX tilde QY EK, it is small, and also more importantly here, if you look at phi star B and C, this is small. Now you may say, well, why phi star B? Why not phi star A? Well, because we want our set to be more reasonable, and you see, because of this, A and B agree up to K at least, and we want to take advantage of that, and somehow force this to propagate all the way up, and actually to make to get this epsilon approximation. All right, so now this set is closed. And whenever I say closed, I mean the same topology, right? Topology that we fixed for this set X once and for all. Now we want to look at another set. And you see, what was the point, again, at looking at YB here? Well, I said for YB in XDN, but really, all that matters is those YBs which belong to one of those FKNs, because they are dense. And the entire condition here, you see this delta being big and these norms being small, any relevant condition is witnessed by something in some FKN for sufficiently large K. So really only those YBs that belong to some FKN matter. And that's what we do next. So we'll let Zn be the intersection over all J of the union of W, Y, B, K of J, where YB ranges, as I just said, just over F of K of Jn. I hope that this is visible. Let me just make sure that it is visible. This is F K of J comma N. Okay, so what do we have here? These are closed sets. Each of these sets is closed. Oops, that was the wrong tool. Each one of these is closed. So it's union. Now union is countable, right? Because we are taking. Why do I have this union sign here? Oh, I see, right. So yes, sure. YB ranges over this, but you see, this is a finite set. So this is still a closed set. So, well, this is supposed to be F sigma delta, not closed. Okay, so this looks too good to be true. This set is supposed to be just F sigma delta. Although why not closed? Actually, come to think of it, there is nothing contradictory. So maybe it's even closed, but in any case, it is Borel. Right, because we have countable intersection here, and we have some closed sets. So we have a Borel set, and now once again, what is that set? So Zn is a subset of what? Well, you see it's pair AC, so it's subset of dx tilde cross bh less or equal than 1. And here we have claim. Claim 1 is that for every n, if x tilde a belongs to x dn, then a comma phi star of a belongs to Zn, right? So Zn is big enough. Now, what is the reason? Well, we just need to check. Oh, yes, of course, intersection. Yes, now I see what was missing from this notation. So we take union. Ah, this is bad notation. Ooh. Okay, so intersection overall m union j greater or equal than m. Yes, right. So we do have to have countable union of sets here. So we look at these over. So basically, we are looking at those w, y, b, k, j's that pass infinitely many tests, right? Okay, yeah. Okay, so let's check. So we need to check that a comma phi star of a is in Zn. Well, basically, that's equivalent proof. So this is equivalent to saying that for all but finitely many j, a comma phi star of a belongs to w y b k. Actually, I should say y b k j. For some yb in fkjn. Right, so this is exactly what I need to prove, and let's just try. So we just need high enough, large enough kjn. So here's the set wybk, right? So if you okay, so it's maybe time. You can look at this. I'll just get my charger and be back in a second. Okay, this is good sign. I didn't break anything when I was getting a charger. So, all right. So as you can see, put phi star of a in place of c. Now, this condition, basically, you can approximate it as far as you want by this, because these EDNs are dense. So the first part, this first claim, is the consequence of the fact that the union of fkj's is dense. That's all we need, right? So Zn is big enough. Second claim. Second claim says that if AC belongs to Zn, then Qx tilde C is approximately equal modulo compacts up to 1 over D to phi star of A. Right, so the second condition tells us that this set is not too wide. And for that, we need another page. The proof. Okay, so we have AC in Zn. And now what this means, okay, so actually, what we'll prove something slightly stronger, will prove that P sub n infinity phi star of A qx tilde minus qx tilde c in norm is less or equal than D. Let's first check that, and then you will see what happens, right? So n is the n from the partition. Okay, so otherwise, fix delta greater than 0, such that, okay, now I'm going to use my skills in copying and pasting. So such that this here is greater than 1 over D plus delta, right? If it's not smaller, then it's sufficiently greater. So this hold, and also fix J, which is sufficiently big. Now, sufficiently big means greater than maximum of n and 2 over delta. Right, so J is this index of these kj's. And now, and also fix YB in f of kjn, which approximates everything up to up to what it needs to approximate it. So that we can just say it shortly, so that A C belongs to W of YB K of J. I don't know, maybe it's a good idea to go back and just copy this set W so that I can show off my cutting and pasting skills again. I think I can put it here. Oh, sorry. Right. Okay. Okay, I hope that nobody's watching this on a smartphone. I guess it may be too small. Right, so this part we don't need. Right, so here's our set. Now, what do we have? So Y, basically what this means is that Y approximates everything up to more than K. And now what do we have? Now remember that we are in a homogeneous set. So well, no, not homogeneous set, actually, no, it's just from the assumptions. We have that the maximum of norm of Pn infinity P star of B minus C Ek of J, and the second one is Pn infinity Qx tilde minus Qy, again Ek of J. Both of these are less or equal than 1 over K of J, right? So that's just to highlight, it's this guy here. And we chose J big enough, so this is less than delta. Okay, now we use the homogeneity. We have that X tilde A and YB belong to this color M1 dN. And now, why do they belong there? Remember that there were those, we had this disjunction of three conditions. First condition was conjunction. No, disjunction. First condition was that their branches are equal. Well, their branches are distinct, so that's out. Second condition was that by the time those branches start diverging, those second coordinates A and B are identical. Sorry, are distinct. Well, no, that's also fine. So A and B agree up to that point because that's this part here, right? So this delta is greater than K. So what must happen is that third condition has to fail. And now third condition is conjunction, right? So both of those norms are small, which is exactly what we want. Hence, okay, so what is the condition? We have Pn infinity phi star of A Qy minus Q. Oh, this is Q. This was supposed to be Q. Qx tilde phi star of B. This is less or equal than 1 over D. And also symmetric condition. Well, I cannot write both, right? So it's basically with these swapped the other way. Now, what do we have? So writing x tilde delta ky is k if the norm of x minus y ek is less than delta, right? So we care about delta here. What we have? Well, actually, I can probably do it here. So you see first, this one here, the n infinity q star a qy, but actually no, sorry. I'll start with the right thing. So Pn infinity phi star of A Q Qx tilde. Let's see. Okay, so let me just point. This is the difference. You see, Qx tilde and Qy agree up to K. That's how it shows this Qy, right? So basically, replacing Qx tilde with Qy doesn't make any difference here, and this is approximately equal up to 1 over D. So you see, this is, I'm using now this one. Let me use different highlighter. This is this and this. So these two are up to 1 over D equal. So I can write that. So it's P and infinity Q x tilde phi star of B. Okay, and now this is approximately equal. So back to this notation delta kj of Pn infinity Qx tilde C. Now, again, the same reason as a moment ago, phi star of B and C are close because this pair AC belong to that set. So it was approximated by phi star of B arbitrarily well. And now when you add everything up, you get contradiction, right? So we get here delta plus delta. Should have probably said less than 2 over greater than 2 delta. Did they say 2 delta or 1 delta? There was some point. Oh yes, 2 over delta. That's correct. Good. Right. So when we add all this up, we get contradiction, and therefore we have phi star of A is up to compacts, actually up to something more precise than compacts. We had we know exactly from this Pn infinity point compacts, and here is 1 over D. This is equal to Qx tilde C. Right, so you see C itself is not a perhaps candidate for lifting for phi star of A, but Qx tilde C is good enough, and that's fine. Right, so once again, just what happened. So we had this branch B tilde, and we had this very thin set consisting of these kj's, and on that thin set, these finite sets fkj of n controlled exactly what the images of the elements in this D sub x tilde were. All right, and there is one more claim. Any questions about this one? So another claim is that the set Z, oops, sorry if I'm not careful. Okay, the set Zn prime, which is the set of all pairs, so the form A, comma Q tilde of C for AC in Zn, this set is 2 over D narrow. But this follows from the previous two parts. Right, so the previous claim, let me just roll back to the previous claim. The previous claim said that if AC is in Zn, then Q tilde C is approximately up to compacts 1 over D phi star of A. So this is really what you get. Basically, this set here is obtained by just taking the graph of phi star and fattening it up, and it's included in that. So what we have is a set which is 2 over D narrow, and moreover, if I look at union of Zn tildes, this covers the graph of phi, right? Because we proved that for every A, phi star of A belongs to this set. Right, if x tilde A belongs to our set Xn. No, not Xn. No, my iPad is, oh, okay. Not Xn, but actually if A just belongs to the X tilde. Right, so why is that so? Well, each A in the X tilde, if A is in the X tilde, then X tilde A, there exists an N. So for every A in the X tilde, there exists some N such that X tilde A belongs to Xn, and then X tilde A belongs to this Zn prime. Right, so finally, we have our epsilon narrow sequence of sets. Okay, any questions? You probably may want to read the proof once again. I guess it's not, it's actually first time that I'm presenting this proof in public. For obvious reasons, I guess you don't want to present something like this in public, really. Anyway, okay, so this is just more of the same, and I didn't use this. Right, so as I said, there was an example that I owed you, and this is not what I claimed last time. Let me first show it and discuss what I said last time. So the claim is there is endomorphism phi of the Boolean algebra P of n mod phi, which has sigma narrow lifting. Actually, we can do better. It has really what you could call two narrow lifting, that there are just two Borel functions that together cover the graph of the lifting. But that endomorphism doesn't have C measurable or Borel measurable or continuous, basically anything reasonable lifting. So this is not what I promised, right? This is not a C-star algebra. I just assumed that this example that I've known since late 20th century should just work by duality, but never checked it until the last class when I in real time realized that something went wrong. So, okay, so let's take a look at this example. So first, we fix a non-principal ultrafilter on N and define phi. So what is phi here? Phi maps P of N to P of N. Actually, I mean, the codomain is really just two element set, empty set and N. So we map those sets which belong to ultrafilter to N and those which don't to empty set. So this phi is really a homomorphism of Boolean algebras. And moreover, the kernel of phi includes phin. Right, so phi is a homomorphism, and the kernel of phi includes the Frechet ideal. Why is that so? Well, because ultrafilter is non-principal. I said it, yes, here. And now what that means is that when you mod out by the Frechet ideal, you still have something. And now, okay, I shouldn't call this phi. Actually, phi is a lifting. So you know what, I'll just change this here. So phi star. So phi star is a lifting, and phi is a Boolean algebra homomorphism from P of n mod phi. Well, really into two element Boolean algebra, but you can say it goes into P of n mod phi. And now it has its graph is covered by two constant functions, right? So it is two Borel, but I claim that it doesn't have a continuous lifting. And the point is that if you have ultrafilter, it really respects, it behaves horribly with respect to bare measure or Lebesgue measure or Haar measure or whatever. Bare measurability, not bare measure. The point is that if you have an ultrafilter, then for any non-empty basic open subset, both intersectional residue and the difference V minus U are non-meager. So the point here is that at the map that sends A to the complement of A is a homeomorphism, and it sends U to its complement. And moreover, for every for every, if you look at, one should really say this in terms of group action, but let me not say, well, you can. Okay, I'll just say it without writing it. Just think of the idea of fin as a group. It's really isomorphic to the direct sum of countably many copies of Z mod 2Z. And fin acts continuously on the power set of n. What is the action? Well, if I have an element of fin, let's call it B, and if I have set A, the action is really just taking symmetric difference. Right? You can just check that this is a continuous group action, and the orbits of this action respect the ultra filter. Right. So the ultra, I mean, so U is fin invariant. So what that really means, let me just roll back here. If you have a basic open subset, this action is transitive on those. So it moves this basic open subset to complementary subsets, and yet filter stays where it, ultra filter stays where it is. So basically that means that V, okay, sorry, I'm making this horribly complicated. So what this means is that for all S and T, which are in 0, 1 to n, okay, for every n, U intersected with basic open set S is non-meager if and only if U intersected with T is non-meager. And the same for the complement of U, because these are acting by homeomorphisms. So from there, you can just see that there is no, that U is badly not Borel measurable. And then my iPad every now and then refuses to scroll. This is funny. So if anybody knows what's, okay, now it works. Because of that, you can check that there is no continuous lifting for this. Now, I don't know the answer to the question to what I claimed last time. So if you have an endomorphism of L infinity mod C0 and sigma narrow lifting, does it have to have a continuous lifting? You see, the hope was that this example just immediately translates into that, but it doesn't. What it gives you, so you see, note, so what phi gives, it gives psi, which maps L infinity to L infinity. And what is psi of f? It is limits as n approaches to UF of n. Now, this is not norm continuous. This is norm continuous. What am I saying today? This is norm continuous, but it is not weakly continuous. Right, so it's very weakly discontinuous functional. And therefore, and when I say continuous, I mean continuous in weak operator topology, although in case of L infinity, it's really weak star topology, which comes from C0. So this is not weak star continuous. And after thinking a little bit about this, it seems to me that the answer is no. And if the answer is no, that may actually help perhaps simplify some of the proofs. Anyway, we still have a few minutes. Any questions? All right. So basically, I have 2 lemmas left. Now, for the next lemma, I need the result from descriptive set theory due to Novikov. If you have Polish spaces X and Y, and there is set which is analytic, so here it is. Right, so it means that it's continuous image of Borel subset of some Polish space. Then the set of those coordinates here, such that this vertical section, so AX, I should say what is AX. AX is set of all Y, such that the pair XY belongs to A. right? So this here is AX. If you look at all those coordinates such that AX is non-meager, that set is analytic. Right, so this is somewhat surprising because non-meager is not really a nice quantifier here. All right, so I can state the next lemma, and yeah, let's see, maybe even prove it. Let's go. I mean, unless you're tired, we can go with this one. I mean, if you're tired, you can try to slow me down with the question. If not, I'll go. Okay, right. So we have phi is an endomorphism of Kautian algebra. D is greater or equal than 1. E is in part of n, and there is a 1 over D narrow analytic set Z subset of dx tilde. Z subset of dx tilde cross BH less or equal than 1. So it's similar situation to what we have as the output of the previous lemma, except that here we are just talking about 1 over the narrow analytic set. We don't know how good it is. Then for every A subset of X tilde, such that both A and X minus A are infinite, at least one of the following applies. Option number 1, there is a C measurable 3 over the approximation phi on the A. Right, so we have this infinite set. On it, we have approximation. We lose a little bit, go from 1 over D to 3 over D, but it's good. And second option is more complicated. There is a subset B of X tilde minus A. Let me try to draw this. So here is X tilde. Here is A. Second option says that we can find a B. So B is still infinite. And there is a little b. So here is a little b inside B. And now both B and X minus A union B, which is this guy here. It's this guy here. They're both infinite. And moreover, any uniformization C of Z, Z is our original set, and also one more, C which belongs to this D. So C is here. C belongs here in the sub X tilde minus union B, and it has the property that A plus B plus C is in domain tilde. So I forgot to say that A was, let me use yet another color for A. So here's A, little a is here, right? So the union belongs to domain of C. C of A plus B plus C times QA is not equal modulo compacts up to 1 over D to phi star of A. Right, so now you see left-hand side, this is equal modulo compacts to phi star of A, because QA times QA times A plus B plus C is, sorry, PA times A plus B plus C is just equal to A. So what possibility 2 tells us is that if possibility 1 fails, then we can somehow prevent our set Z from having approximation, uniformization, because quantifier on C is that for every uniformization C of Z, there is some obstruction. Right, so we have 12 minutes left, but it's actually a short lemma, so I think I can do it. So basically, here is the proof. All right. We take V to be set of all triples A, B, C. So, okay, right, so we have, here is X tilde, here is A, and here is the complement, all triples A, B, C in this, and C belongs to the codomain, such that there exists C prime in B of H, such that A plus B, C prime belongs to Z, and C is up to compacts modulo 1 over D equal to C prime QA. right? So V is a set of candidates for for lifting. Now this set is analytic. Right? Why is that so? Well, it is just because the only parameter here is Z, and no. Yeah, maybe it's better to do this next time. So instead of to rush, no, I'm just having some doubts about this QA here. Yeah, okay. So let's just leave this for the next time. Right. So next time, basically, we're finishing the proof and starting a few more other topics. So maybe it's better if I just say a few words about the homework. I guess we can say that. So here. Oh, okay, good at this. Sorry. So ignore exercise number 1. I forgot to. All right. Okay. Yeah. So actually, I'm not going to say anything about the homework except that I'm going to revise it in a moment. So don't upload it yet. This first question is not good. Yeah, the other questions are better. So yeah. Okay. Okay. So I guess unless there are questions, we can just stop here, and I'll see you on Friday. Okay. So bye.